So we're talking about matrices for week 4, and this is the what you need to know. Last week we talked about size. It's not really big or small, but we talk about the order m by n, where you can have rows and columns. We also talk about properties and behaviours, where properties is how they work and behaviours is how they relate to each other. Now with all of that, we have special zero matrix, which is any square matrix where all the elements are 0, and you get these particular properties that hold. Really useful. But yeah, like most things, 0 is a bit boring, but overly complicated at the same time. What we move on to now is an idea of an identity, which is the simplest non-trivial diagonal matrix, such that this particular property holds. And what's important here is that you notice that the x remains unchanged. We've multiplied it pre and post by something else, but the actual number hasn't changed. It's like how in our whole number system, and when we times by 1, you can times anything you like by 1, and the number remains unchanged. Identity matrix can be, it has to be square, and it can be 2, 3, 4. In fact, it doesn't really matter as long as it's square. It's important because to remember that all the diagonal elements are 1 and all the others are zeros. Well, let's just digress back to properties for a moment. We have to consider the different types of laws, and we're talking about associative, distributive, and commutative. What we're looking at here is whether these laws hold for addition, for subtraction, for scalar multiplication, or matrix multiplication or matrix involvement. So as you can see here, associativity is true for addition but not for subtraction, true for scalar multiplication, and true for matrix multiplication. The distributive law is when we're distributing out over brackets. That's kind of like how you were used to in an algebra of expanding brackets. You can see that it's true using scalar multiplication and addition, and for subtraction. It's also true for matrix multiplication with addition and subtraction. Commutativity is when we change the order, we want to see if things still hold. So you can see that it's true for addition but not subtraction, true for scalar multiplication but not true for matrix multiplication. It moves on now to the multiplicative inverse. Now the multiplicative inverse of any number is whatever we multiply that particular number by to get the answer of the identity element. This is why the identity element was so important. So for example, in our 6 by 1/6 equals 1, you can see that 1/6 is the multiplicative inverse of 6 because we get the answer of the identity. In matrices, we can see that we wanted to have a times something equal the identity element, and in fact we call that something the inverse of a, which we write as a to the power of -1. We also call a invertible if and only if those particular properties hold, where we multiply a by its inverse and we get the identity. If an inverse exists, we sometimes use that notation for there exists an inverse. So I can hear you saying, yay, that's great, now we can have inverse of matrices, but how do we actually find it? Well, we find it by, for a 2 by 2 for example, using this particular formula, where the inverse is fractional scalar at the front, and we rearrange the elements like so. This particular fractional multiplication bit at the front here we call the determinant. It actually determines if the inverse exists in this 2 by 2 matrix. The important part is this AD minus BC, so maybe you could pause and consider what happens if that equals 0. Go back and look at where it falls into the actual inverse of the matrix. So if AD minus BC equals 0, we call this particular matrix singular, which means it has no inverse. It's quite an extended and heavily algebraic proof for how we develop that rule for the inverse of a 2 by 2 matrix. It starts off a bit like this. It starts getting very, very complicated. This is in an augmented matrix using row-reduced echelon form. If you're interested in this, you could look it up. But basically, it just proves that the inverse is what I said it was. It's really important to remember there is no division in matrices. Division as an operation is not defined. What we can do, though, is we can only pre-multiply or post-multiply. Pre meaning before and post meaning after. And this is really important. So for example, if we wanted to isolate matrix B in this particular equation, we have to pre-multiply by the A inverse on both sides, then post-multiply by C inverse on both sides, and then you'll be able to see what that means. There's a special case here for AB to the power -1. You can have a look at that, but that's basically what you need to know for week 4.